But the point I'm trying to make is those two bearings right now, as they are set up, they have infinite stiffness in the XY plane to each other. So they cannot move. And this is why structures like this can be perfectly fine and happen, because if you can make sure that this point does not move in respective to this point, then this structure is not really having any buckling issues, right? Hey guys, welcome to this module number 7 of the Inspire course kit. Can't wait for this module because it's optimization, especially topology optimization, which I am a big fan of. So let's dive into it. First of all, let's check quickly in the course kit what this will cover. So we have supports again, we have geometric modification. I will talk about this in a minute. Material definition as always, and contouring. And optimization, we have optimized shape and polynerbs. So this is more or less a topic which we cover in this video. So basically, first of all, Eric did a fantastic video and I recommend to you to check this out. Basically, I would recommend to you to first watch the whole video done by Eric and then come back to this video because I will have some comments on this, and so I think this will be the best for you. All right, so basically, what Eric did on here with the topology optimization, I had a couple of comments, which I just coming from a hypermesh background, you always have to be aware of that. So some things what can bite you in the meshing process is those little gaps or steeps or whatever you would call them, so this small features here, they could cost you, and you can get rid of them pretty easily. So I would, if I would have to topology optimize this, I would do just a push operation, click on here, and then drag it, and you can drag it to a point of the surface area. Basically the center would be the one I would pick, and then let go, and you're done. So this gap is removed, and so it's easier for the solver to mesh it, because there's no need to do some little elements there because of the geometric feature. The other thing, which also is pretty important and interesting, is some things like this. I get that all the time with my students, so that if you have a very steep or sharp edge, this is also very, very difficult for the solver to put meshes in here because they get small to infinitely small, and so it's pretty hard for the solver to do this. So if you partition this, rather than partition it with the tangential line, you could partition it with a little bit of a bigger line. Let's see how this goes. You click on this, for example, and then as a size, let's just say 8. And you see, this would be the edge you would have to deal with the tangential line, and this would be the edge. See how it loses its sharpness, its steepness, or however you would call that. So it loses the edge, and so that means it's easier for the solver to handle that. So that would be my two just comments to geometric modifications. And then let's quickly look at the model, how it's set up. Don't save. Right, I will just load in the results. I mean, by now I think you all are fine creating supports and forces. Yeah, so basically what I want to show you here, let me show you the topology optimizing part, and yeah. So there's a lot we could go into, but just from an optimization perspective, some things which I think are crucial to get it right is to properly understand what the supports are doing. I have the results here, right? So I could look at that and just judging this kind of structure. What would you say as an engineer? Does this look like a good structure? Well, it definitely is, because the analyzers told us that it is alright, but there is something which caught my eye, and I could not see past that, and that is this structure here at the lower left, lower right. That seems a little bit, that seems like it would buckle very easily. I stumbled upon this in post-production and just wanted to clarify, it's not just an alright structure, as if there were many possibilities it could go. It's the optimal structure. The best structure in the domain or design domain under the given boundary conditions. Because it's an optimization algorithm, gradient based, and as long as the mathematical design domain is well defined and you can reach the global minimum with a gradient based solution, then you are 100% sure that this structure it proposes to you is the optimal it could find under the given constraints. Structural constraint as well as the design constraints, like how much material you have given the solver. So basically, whenever a structure is not making too much sense to you, the first thing you should do is check the boundary conditions. And that's the same thing we are doing right now. So off you go. So what I did first was to just get to the part from the result. Yeah, I think it looks even more dangerous here. But let's just imagine how this buckles. Well, what I did was just run a buckling simulation. We covered that in module 4, I think. Yeah, module 4 was the buckling analysis. So I did just run a linear buckling analysis, and I was astounded did not find any buckling modes in this area. It did find the other ones with other structures, like for example in here or in here, but not really this one. And the reason for that is that the buckling length, or the length in distance, is not too big. So that's one thing. But the other thing, which is far more important, and that's the point I'm trying to make, is that you really deeply understand your constraints. So the constraints here, they say you would like to constrain this so it could rotate. So this surface can rotate, but it cannot move neither in Z nor in X nor in Y. So that would be a fixed bearing. And then this would be more the loose bearing, but with quotation marks, because here you let free the Z rotation and the Z displacement, right? So if I click here, on this one, you can see in the constraints that the translation in Z and the rotation in Z is free. All others are fixed and they cannot be really changed here. I tried different things, and maybe somebody of you can come up with an even better solution, but some things did not work as I would like to. First of all, I just put a connector there and tried to constrain the master node. That did not work at all. I could not select the master node. But besides that, what's even better in circumstances like this is to model out the part which is underlying. So that means the part it connects to, the part which holds the mounting points. If those are two different parts and not structurally connected to each other, it's also a different thing. But the point I'm trying to make is, those two bearings right now, as they are set up, they have infinite stiffness in the XY plane to each other. So they cannot move. And this is why structures like this can be perfectly fine and happen, because if you can make sure that this point does not move in respective to this point, then this structure is not really having any buckling issues, right? But just looking at it, you must just judge the structure of what you see and try to make sense out of it, and see then the underlying cause, like in this case the bearing scenario. So what could you do? And this is just also like an input from my side to just throw it out there, and you can take this idea up and explore it for yourself. I did not fully investigate this, but what I did here is I just made a simple part with a couple of sketches and extrude. Yeah, maybe I should have trimmed it a little bit, but yeah, just a structure which is a representation of the stiffness between those two, right? So maybe it's too less stiff, maybe it should be connected here too. I don't know. That depends completely on the situation. what this part is should look like, right? So this is being done then, and then what else is also important to do is, besides constructing this part, is also that you prevent the motion in set somehow, because as you saw, I did lose all my constraints here. So there's no constraint which prevents the motion in set, which I have in load case 1. So basically it's an unconstrained model, and that's why I should have something like this bearing, or I should have moved the surface up here and did a contact here. So how does this even work? This works with contacts. So basically you have to go into the contact settings and then check that the contacts which you have here are sliding, because likely they are sticking or frozen in this case, which is not ideal. You would want to have them sliding. And then you can do your topology optimization like I did and see the difference. So basically I can show that like, isn't it there anymore? Here. I think I did 2. That was a mistake. Alright, so this is what I get. And see how the structure differs. So this is now a straight line, which I like quite a bit more compared to this S line. And also see that it did go to the edge here, which in my engineering mind also makes a lot more sense to have it go to the outer boundaries because of the effects you have for the stiffness. Like, yeah. Alright, so what is in there now? So really make sure you understand your constraints for setting up an optimization, because those constraints, they fully describe how your part will look like in the optimization, and there can be a tremendous influence of the performance of the part. So I did not fully investigate this, so what should be done here would be doing an analysis on this part, just comparing it then with this, or also putting this part as it is in a scenario like here, where you have like a stiffness, a finite stiffness between those two bearings, which is not infinite. So this should be done, or could be done, but I'm leaving that to you. Experiment with the model, and you can see that's also why I like topology optimization this much. It's like you can experiment and just explore the design space and see what makes sense, what doesn't, and come up with other ideas, other constraints, other load cases also especially, and come up with a solution which is even better than the one before. So it's a constant struggle or a constant moving forward into the optimization space and find the best possible solution you can. And this tool, topology optimization, is such a great help exploring the design space and exploring what structures could be done. So I very urgently recommend to you that you check this out. Check topology optimization out. There's a lot more topic we could cover. For example, different shape controls. I can cover them briefly, but you can watch a lot of other videos on my channel if you would like to get some sort of more education on topology optimization. But just briefly to cover it, so what we did here was a topology optimization with an extrusion constraint. That means that this part which comes out has more or less a constant cross section over the set direction or thickness. So what else you could do with the optimization constraints or shape controls is, let me go to, where is it? Structure, and then on shape controls. Also be careful, there's two things here. There's shape controls like draw directions, and there's also shape controls like symmetric controls. So if you want to have a symmetry, this is the icon you would like, and then if you want to have something like the draw directions where the extrusion constraint is one of those, you click here. And you can see now you have single and split draw. And just briefly talking about these. So single draw means like, just think of you have a milling machine. And this milling machine can or must make this part. And it can't just draw or mill from one side. And it also cannot change its angle. So it will just mill down like the extrusion, but from one side. it can leave a closed surface, for example, here at the bottom, and drill out the holes from the top, for example, if you would like that. The split draw is the same thing, but you have two sides here, right? So you can go from one side or the other. This would be fine to, for example, have a constant surface in the middle and drill out the holes from both sides. That's that. Then radial is the same thing, but it goes around, right? It changes the angle here. Extrusion we covered. And then overhang is for 3D printing parts. So that means you have a overhang constraint angle, so the printing can work fine. And then you have milling, which is more like a complex combination of the split, but now in all three directions. And what this will do, you can see that very good and optimization progress. It will first of all create like little holes, and those holes will then grow and then form structures. It's like almost like from, but I'm talking now here maybe rubbish, but it's also almost like a level set approach. Maybe it is. I'm not 100% sure. But this milling is a good way of having a lot of freedom to create it, but still make a part manufacturable. That means you choose to do this to give the solver a lot of freedom to choose your part, but you don't want to have any constraint where you have that like a structure which cannot be reached, or a structure which can only be done with 3D printing. So for example, if you have a structure all around, but in the inside there's like a hole, and you cannot really do that with milling. So basically those shape controls, they help you design constraints on the structure which comes out of the optimization, which makes the part manufacturable for traditional manufacturing. 3D printing, you have the overhang constraint, but then that's it, right? So 3D printing part has no problems with those kind of undercuts, as they are called. So basically, those are shape controls you could use to make the part manufacturable, and they help you greatly in designing the structure afterwards. Yeah, and then symmetry should be explanatory, self-explanatory. You have just symmetry planes, you have cyclic symmetry, or cyclic symmetric symmetry, and you can define those, for example, to make something like a wheel or so, where you have a cyclic symmetric part or so. Yeah, so basically that's about it. There will be a lot more topics to cover for optimization, because we just now did a little bit of a dive into topology optimization, but there is also topography optimization, which we covered briefly in one of the modules. But then it's also gauge optimization, topography and gauge combined, and PolyNURBS shape optimization. So there's a lot more to cover, which we might do in upcoming modules for the Inspire course kit. But for now, the optimization intro as it stands should introduce you to topology optimization, which is, in my opinion, the one you first should explore and the first one you should apply to your designs. Because topology optimization really needs just a design space and load cases. That's it. So you could design, or you could start with topology optimization very early in your design stage, and that's why it's also so important to do. All right, I think that's about it. So just summarizing, be careful with those little gaps, right? They could bite you. Be careful with the sharp edges, and also be careful with constraints that have infinite stiffness relative to each other. Be sure to make a double check that you have, for example, if you have a stiffness between those two, that the structure which comes out is not completely different. And also, please check buckling. That's so important, because you're doing a linear static optimization that does not take into account nonlinear effects. So buckling should always be on the top of your mind for checking your optimized designs. That's it. I hope to see you in the next lecture or next module. And if you have any questions or comments, please leave them down below. And I'm happy to see you in the next one. Bye guys.